Hello everyone. So today we have a very interesting integral to compute. So this question was presented to me during one of my TA sessions in my university, and I went directly solving using the normal CU substitution integration by part and trying to come up with a constant and then taking u and v dv du, and at the end I discovered I was in a loop of not reaching to the final answer. So here is the solution, and I think the only way in which we can approach the question, at least for now, is through a trigonometric substitution. So how can we do that? So in order to solve to get to the solution of this integral, let's consider the trigonometric substitution, the trigonometric identity sine square theta plus cos square theta equals to 1, and cos squared theta minus sine squared theta is equals to cos 2 theta. And there is also another identity, 2 sine theta cos theta to be equals to sine 2 theta. For this introduction, we are simply going to need just the first equation. So you have to have these three trigonometric identities in your mind in order to come up with the solution to this integral. Now we are going to name this our equation star because everything is going to be based off that. So once we have this, let's come up with the solution. We say from equation 1, we notice that sine squared theta can be expressed as 1 minus cos squared theta, meaning that sine squared theta can be expressed as 1 minus cos squared theta, right? This is from equation 1. We can call this equation 1 star because that was derived from equation 1. So if we take a critical look at this equation 1 star, we notice that it is very similar to our original equation star, right? The only difference is we have 8 here and we have 1 here. We have x squared here and we have cos squared theta here. So how can we include a constant such that we can simply insert anywhere we see x, we insert here, it should give us exactly what is in our equation star. So the only way in which we can do that is multiplying all through by 8, so that we can have 8 here and 8 here, a negative and negative here, and a constant value here multiplied by cos squared theta, so that we can easily let x to be that value here. So to do that, we can simply multiply the entire equation 1 star by 8. So doing that, we're going to have 8 sine squared theta to be equals to 8 minus 8 cos squared theta. So we haven't changed anything in equation 1 star, right? So we notice that the 8 is the same as the 8 here, the minus is the same as the minus here, and the 8 here. Though it's not the same, we can actually create or transform it to be in the form of x squared. And how can we do that? We can write this as 8 minus 2 root 2 cos theta, all that squared. We can write it in this form, or better still, we can write it as 8 minus the square root of 8 cos not squared, this, good, cos theta. Now all of that squared. We notice that the 8 here is the same as the 8 here. This can be represented as the squared, right, the x. So this is like the 8 here, and this is like the x squared, and this is exactly this. That's the whole purpose of the substitution. How can you express your trigonometric identity to look exactly like the integral that has been given to you? Now once we have this, then we are going to move forward by saying this simply means that 8 is equal to 8, minus is equal to minus, therefore x will be equal to therefore let's change, x will simply be equal to the square root of 8 cos theta. As simple as that. And once we're able to deduce this simply means x squared will be equal to 8 cos squared theta, right? Once we have this, we can look for the derivative here. So looking for the derivative here, so dx will be equal to the square root of 8 and the differentiating cos theta we have minus sine theta, and this is with respect to theta. So we are going to call this our equation 4, right? And we notice that we have our the x with the x, we have our substitution of x here, and we have our substitution of x squared. So we are going to insert all of these formulas in our original integral, and if we do that, we are going to have this. So doing that, we are going to see that we have the integral from 0 to 2 of the square root of 8 minus our x squared is 8 cos squared theta, and our dx from here is minus the square root of 8 sine theta d theta. Good. So that's what we have for now. I'll just have to create some space. Good. Now after having this, it's all about simplification. We already saw from above here that 1 minus cos squared theta is sine squared theta. So we notice here that 8 is common. We can factor the square root of 8 out. We'll be left with the integral from 0 to 2 of the square root of 1 minus cos squared theta, which was the whole idea behind taking our substitution to be the square root of 8 cos theta, such that we can do this step so that this can simplify to be something like sine squared theta. Now we notice out here we have the square root of 8 sine theta d theta. Now we can further simplify this as the square root of 8. We notice here that there is also the square root here, so if we bring it outside here, we're going to have the integral from 0 to 2 of 1 minus cos squared theta from above here is sine squared theta, right? We're all clear with that. Once we have that in mind, then this will be sine squared theta square root, right, multiplied with this will be multiplied with, since this already came out here, we're going to be left with sine theta, and all of that is with respect to theta. Now continuing with our computation, we see that the square root of the square root of a multiplied by the square root of a is simply a. So this simply means that we are going to have minus 8, the integral from 0 to 2 of the square root of sine squared theta is sine theta, and sine theta times sine theta is sine squared theta, and all of this will be, we see that everything is simplifying down to its simplest form. So we are at this point of having a trigonometric function with a power, and when integrating trigonometric functions, it is usually very complicated to integrate directly trigonometric functions with power. So the thing we usually do or normally do is to convert the power to a double angle identity, and that is where the use of this formula, the second and the third formula, are going to come in place. Specifically the second formula, because we can express sine squared theta as cos 2 theta, which is a double angle identity, and we can now easily integrate that. So what do I mean? What do I mean by that? We already know that the identity is cos squared theta, right, minus sine squared theta is cos 2 theta. We also saw that cos squared theta plus sine squared theta, or better still, sine squared theta plus cos squared theta was 1. We want to substitute sine squared theta, right? So we are going to, from this equation, we see here that cos squared theta is same as 1 minus sine squared theta, just as what we saw from above here, from here, right? Just like what we saw from here. So it's still the same application, and having cos squared theta to be 1 minus sine squared theta, we are going to substitute this equation 3 in equation 1. So if we call this equation 1, we call this equation 2, and we call this equation 3. If we say equation 3 in equation 1, and the whole idea is that we can remove the cos square theta here. So we are going to have cos square theta is 1 minus sine square theta, and this will be minus sine square theta to be equals to cos 2 theta. So meaning that 1 minus 2 sine square theta should be equals to cos 2 theta, right? Further simplifying this, we see that 1 minus cos 2 theta should be equals to 2 sine square theta, meaning that 1 minus cos 2 theta on 2 should be equals to sine square theta. Now that's the whole idea of using the two trigonometric identities to simplify our power or our trigonometric function in terms of power into a double angle, because with this we can easily integrate this. So instead of looking for the integral of sine square theta d theta, this can be written as the integral of 1 minus cos 2 theta on 2 with respect to theta. So that's what we are computing. We can further simplify this as the integral of a half d theta minus the integral minus a half the integral of cos 2 theta d theta. So we further simplify this as well. This the integral of, remember our limits is from 0 to 2, from 0 to 2. So here will simply be a half theta, and here also a double angle identity in terms of sine 2 theta, and that was sine 2 theta from equation 3 is 2 sine theta cos theta, and that is where it's going to be very useful to us. What do we know? We know that sine 2 theta is 2 sine theta cos theta. So let's forget about this for now and concentrate on simplifying this function, meaning that we are going to have we are also going to just ignore this constant for now. This is for the sake of the video, but when answering this for exams, it's completely different. The approach is different. So we know here that we can simply substitute this here, meaning that we are going to have sine 2 theta to be 2 sine theta cos theta, right? And now what do we know? We know that we initially made a substitution. If I could quickly go run to that substitution. The substitution was x equal to, this was our substitution, x equal to the square root of 8 cos theta, right? We saw that we made a substitution x to be equals to the square root of 8 cos theta. So this means that x all over the square root of 8 to be equals to cos theta. We have our value of cos theta. We can easily substitute it here in terms of x. But the problem is we do not have our value for sine theta. How then are we going to get this value, which is the main thing? We have to do. And in order to get that value, we are going to use a right angle identity. And also these are all trigonometric identities. We know of SOHCAHTOA. If we know of this, SOHCAHTOA, meaning that when we're dealing with sine is the same as opposite over hypotenuse, cos is the same as adjacent over hypotenuse, tan is the same as opposite over adjacent. So if we know that cos theta is adjacent all over hypotenuse, and we are going to consider our angle here to be theta, right? And we know our value for cos theta. We know that cos theta is x, and x is our adjacent, and adjacent is usually the angle down. So here we're going to have x, and then our hypotenuse is the square root of 8, right? The square root of 8, that's our hypotenuse. And also we also know there is an identity which says that hypotenuse squared is equal to opposite squared plus the adjacent squared, right? So meaning that we can get our opposite, which is this, right? We can get this value here. We don't know it. We don't know the value by simply taking the hypotenuse squared minus the adjacent squared, or that square root. So if we do that, if I will have to create more space here, just a little bit space here, we're going to notice here that this, right, can be written as hypotenuse squared minus the adjacent squared. And from our values we had from cos theta, we saw that the hypotenuse was the square root of 8, and since we're taking the square, it will be that minus the adjacent, and the adjacent was x, right? And it will be x squared. So this is actually opposite squared, not just opposite. If we want to get the opposite, we take square root. So meaning that our opposite, which is the angle we are looking for, will simply be the square root of 8 minus x squared. So instead of writing opposite here, we're simply going to write the square root of 8 minus x squared. So from here we can get our sine theta. We know that sine theta from this, sine theta is the same as opposite all over hypotenuse, meaning that sine theta will be our opposite. Opposite to this angle is the square root of 8 minus x squared divided by the hypotenuse is the square root of 8. So our worry of our red question mark here, sine theta, is simply the square root of 8 minus x squared divided by the square root of 8. So meaning that here we are going to write this as 2 into the square root of 8 minus x squared divided by, remember that the square root of 8 is the same as 2 root 2, such that we can simply cancel this, and our cos theta, as we saw, is x all over the square root of 8. So everything is beginning to make some sense, right? So we notice now that let me bring down this, right? Good. We are at a point of simplifying our sine 2 theta. So this was sine 2 theta. Sine 2 theta was this. So meaning that we can safely write this as x, the square root of 8 minus x squared divided by actually that's like the square root of 16, which is 4, right? Now this is our value, right? So we're going to go back to our original equation. I think it should be in yellow, where we are simplifying everything. So also if we know that cos theta is x all over the square root of 2, this means theta will simply be the cosine inverse of x all over the square root of 8, right? So coming back here, we're simply going to, this is equivalent to a half cos theta. Cos theta is cosine inverse, the cosine inverse of x all over the square root of 8, right? Now from 0 to 2, now minus 1/4. What do we notice? Sine 2 theta, we already simplified our sine 2 theta to be, this is our sine 2 theta. So our sine 2 theta will be x, the square root of 8 minus x all over 4. And these are, this we are computing like we're substituting the upper and the lower limits, because we already finished with the integration. Now we're simply substituting, and once we have this, we can simply put in our upper and our lower bound, and doing that we are going to have our final answer. Most of the times they will give you these questions without even the limit, meaning that you end at this point without substituting. But know that what you need to do is simply put in your upper and your lower limit. And with that in mind, we've come to the end of the video. Please kindly support my efforts. Creating this video takes an enormous amount of time, given that I'm a student. I also have other things to handle, and dedicating this time to create this video takes a lot of my time, my resources, and my energy. So it will really help me a lot if you could subscribe, share the content, like, so that it can reach out to more people and I can get noticed for the little work that I'm doing here through this channel, KET Academy. So with that, thank you very much, and if you have any worries, you can put them in the comment section and I'll try to answer them. Thank you so much, and see you in the next video.